coming to Berkeley. I guess I've now been at 5 universities, and this is the one that's really deep in my heart still. I can't say that too loudly. I'm a Bruin, but I have a bear in my heart, I guess. So, yeah, so I want to talk to you today about emerging low-cost sensing. So, I will, look a little bit historically at what we've done with higher-priced sensors, but I think the real revolution that's happening is the low-cost sensing, and also how that fits with a very ubiquitous technology that I'm sure everybody has in their pocket, our cell phones. So I want to talk about what's possible now, and then what we could do maybe in the next 3 or 5 years. And then I'm going to use a series of examples so we can better understand the benefits and the pitfalls of using these low-cost sensors for PM. And I will draw in a couple of other examples that are using gaseous pollutants as well, just to illustrate concepts. So this is sort of the traditional approach to sensing PM. We have, and I'll show you, we also have stationary monitors later, which I'll focus on. But we might use something like this Aerocet to measure particle counts, and then convert it to mass, or micro-aethalometer. These are good instruments, and they produce a lot of really good information, but they're expensive. $3,000 for the Aerocet, $7,000 for the micro-aeth. So if you want to equip somebody with that, you're probably going to put them in a backpack, have them carry them around. They have very limited battery logging capacity, restricts the person's movement, and you're probably only going to be able to do that for a fairly small study, because most epidemiological studies can't equip 200 people with $10,000 monitors. You might be able to use it for a scripting study. This is about 5 years ago in a study I did with John Baums and others, where we were trying to understand exposures faced by bicycle commuters. That's me 15 pounds ago, I guess. And we can detect very dramatic changes as we go through the urban environment. This is a map showing ultrafine particles on a low and high exposure route. And we did hit some points here where we had 1 million particles per cubic centimeter behind a bus at, I think, San Pablo and Ashby. I think I was the one measuring that thing. But what we're seeing happen now, so we've had that evolution, but we have this world that Mark Weiser predicted in 1991 that would become a Ubiquitous world. So we would have the complete embedding of technologies into our everyday lives. And we're now seeing the possibility of having very pervasive sensing of personal activity, physiological parameters, and ambient conditions. And this isn't really being driven by an interest in PM. It's being driven by big money and mobile sensing technologies and telemedicine. The annual market is predicted, in the next 5 years to be about $10 trillion a year for telemedicine. So the types of investments that are going into these low-cost sensing devices that can be paired up or put right on board a phone is enormous. And we now have one phone for every man, woman, and child on the planet. So about 7 billion cell phones, and 2 billion of those are smartphones. And in the US market, the smartphone is penetrated. It's about 68% of the people carrying cell phones are carrying smartphones. And these are really powerful little computers that have a lot of sensors that are already built into them. So they have this central core processing unit, and then you can see the array. I won't read all of that, but very interesting: temperature, humidity, barometric pressure. You can measure heart rate, you can measure oxygen saturation, ambient light. You can measure physical activity because there's an accelerometer built in there, and of course a GPS. They have a display unit, which we've all seen, power management unit, a communications module, and some limited onboard storage. But they can be used for a lot of different sensing. And when we think about sensing, I like to break it down into 2 types. Opportunistic, where we're just going to ask the person to carry a cell phone and load an app on, and they don't have to do anything else. And we can do things like track their location, their physical activity, their trip mode. I don't know, how many people in here use one of these activity trackers for your own physical fitness? Moves or Apple Health or something like that. So, you can use that. It draws down the battery very slightly, but it actually gives, in studies I've been doing in Europe where we've been comparing these to very detailed trip diaries, we get very good information about people's activity levels, where they are, what mode of travel they're in. which can often mean a lot for their types of exposures, as say Mike had pointed out, the very steep gradients around roadways. Then we can get people to participate in a minimal way, and we can measure a lot of things on the cell phone. We can measure their mood or their affect, so if we're thinking about asthma, interacting with psychosocial stress and air pollution, we might be able to know if the person's feeling stressed, the gait, posture, noise, ultraviolet radiation, blood oxygen, heart rate, and even dietary assessment if possible. So then we move down to the next level. We can use the cell phone as a base station. So this becomes a way to communicate and collect information and store it on board. So we're going to have some other sensor, and then the cell phone is going to be hooked through either wireless or Bluetooth communication, so that you're going to draw the information off the monitor and into the cell phone and then put it up into the cloud along the web. Or you can have standalone sensors that are now becoming very low cost, and you can see the wide array of things that can be measured this time. Now, we've just completed a review with my graduate students. We looked at the 25 most popular cell phones, and this is a horribly crowded graph that just shows all the types of sensors that are potentially on board. And what we found is that there is a very large variation in the type of sensor and the quality of the sensor. So we can take the same application like moves and track people's activity on 2 different phones and get very different results. So this really complicates the collection of comparable data for large populations, and it's something we have to keep in mind as a big limitation when we do this, because ultimately we don't want to have to give people equipment. We want them to use their own cell phone. So let me show you an earlier study that my colleagues and I did in Barcelona, Spain, and have now extended, and I'll show you some new results. But we really wanted to test this sort of novel, opportunistic, participatory sensing to see whether we could use it to improve air pollution exposures. And we had 36 people that were equipped with traditional activity trackers. So they had accelerometers, and then they had a pouch with a GPS, the cell phone in it, and then this is another activity tracker that uses galvanic skin response and temperature gradients on the skin to measure physical activity. So we had them do that and keep a travel diary. And what we did is we took some existing air pollution surfaces that were from dispersion and so-called land use regression models. So these are very similar to the ones that Mike was showing, but maybe a little bit more highly resolved. And then we used the cell phones and some of the travel activity information to draw out the mode of travel. And why this was important is because, I don't know, it's not projecting properly, but we used sort of indoor-outdoor ratios from the literature to then infer what the likely concentrations were when they were in these microenvironments. And then we used hourly or daily information from background monitors to oscillate our pollution surface up or down so that we could look at where there, for example, this very high area, how much higher that became at rush hour than it was during midday when traffic was lower. And that allowed us to get a personal pollution exposure assessment. And then because we had the cell phone and the physical activity information available to us, we were able to compute the person's activity level and their inhalation rate so we can get an inhaled dose. And really for epidemiology, that's what we want, right? We make these very strong assumptions in our studies that most people sit outside on their front porch, they don't move, they have a constant breathing rate, and they stay there for 24 hours a day. And as my friend Rick Burnett, who's a famous statistician, says, with all the errors in our data, Mike, it's amazing we find anything. And it's true. So we don't want to continue with that approach if we can avoid it. And I've used it many times myself, so I'm not criticizing other people that are using it, but sometimes it's the best we can do. So this shows 1 day of activity for each of our volunteers. You can see that the metabolic equivalent activity levels vary quite a bit depending on where the person is and what their activity rate is. Maybe they're sitting in a car here, they're walking or biking here. And what we found is that in the travel microenvironment, people were spending about 6% of their time, and this is for NO2, but I'll go on to some PM in a second. They had about 11% of their NO2 exposure time-weighted because the exposure field is higher when they're in the transit environment. But then, because a lot of people walk and bike in Barcelona, and when they're biking, they're inhaling about 5 times more oxygen than when at rest, their inhalation accounts for 24% So this one little microenvironment that we may ignore in most of our epidemiological studies is really accounting for quite a large portion of their total exposure. So we went with this data to the NIH, and they amazingly gave us some more money to do a bigger study. So we did it on about 175 people, and we see a similar pattern for PM. So in Barcelona, 59% of the time at home, 20, similar to American time activity budgets, except they spend more time in other places, and I'm going to say that's the tapas bar effect. So they're very social, and they go out somewhere almost every day. But then when we look at the home, which we use in most of the epidemiological studies, that goes down to about 47%, and we start to see the travel time increasing. And then again, by the time we get to the inhaled dose, travel accounts for a disproportionately large amount. Now for PM, it's not as dramatic a change as it was for NO2, but it is a fairly substantial one. So in this case, does it make any difference to what we would use in a typical epidemiological study? And the answer is absolutely yes. So here we've got NO2, and I'll just focus on the PM. Now, Barcelona is still a pretty polluted place, so 24.6 micrograms per cubic meter, and the home-based exposure goes up to 30, so that's about 22% difference, and it's an underestimate. So there's a potential here that we're going to bias our effects, probably in this instance towards the null, because we're not picking up the higher end exposure that's going to tilt our curve up a little bit more. So it's a significant problem, and I think what this shows is that we can use cell phones to enhance exposure assessment. And this is before we get to the sensors themselves, just with the onboard location. The other thing we discovered is that you get very big data fast. So measuring every 10 seconds with 2 sensors on 174 people, you get more than 10 million observations a week. And they're messy observations. They have air in them because when someone walks inside a building, you start to see that signal from the global positioning system degrade, but you can't tell if the person's actually walking out to get a coffee next door or if it's a degradation of signal. So we spent a lot of time working on algorithms to clean that up. There's a new precision medicine cohort that's supposed to be formed by the NIH with 1 million people. So they asked me to do a talk for them, and I did the same calculation, and for that you're getting more than 60 billion observations a week. They're all very messy, so you do get very big data. So I think the lessons here are that we can use location and physical activity to accurately be measured on a cell phone, that this information can really improve our exposure assessments when it's fused with PM exposure models, but that the data are very big and very messy and very time consuming to work with. Okay, let me shift now to actual sensors. In 2014, Schneider and her colleagues published this paper, The Changing Paradigm of Air Pollution Monitoring. Paradigm may be a little strong, but it is a major change in the way that people are approaching monitoring. So the current approach is we might use those research monitors I showed you, or have these stationary sites that measure a lot of things with high precision. It's limited to government, industry, and highly funded researchers. It might be that there's compliance, monitoring, enforcement, research, and then government websites, permits, records, that sort of thing. Here, you're really expanding the use by communities and individuals. There are new and enhanced applications that are coming with this, where people might want to know about their own exposures. Say they're asthmatics, they want to know if they're walking through fields and that are more polluted, and that there's increased data availability and access that's not controlled centrally by a government. And when we look at PM sensors, this is, it's almost embarrassing to say things like this in front of Kathy Hammond, who knows far more about these types of instruments and measurements than I ever will, but we can break it into really 2 broad categories. And one is that we have some filter-based instrument that's going to draw the particles through a size-specific inlet or cyclone and deposit particles on the filter for post hoc analysis. So you can either weigh it, you can do chemical speciation, or both. And the other is some light scattering. So we're going to bring the particles into the monitor and scatter light across, or put light across them and see how it scatters, and it be lasers or other light sources. And we're going to see how much the particles attenuate the light. And then there is a hybrid of this, which is the aethalometer I showed you, which is pulling in the particles onto a tape and then looking how dark that gets. Sort of coefficient of haze is the original one, and the aethalometer is an extension of that. So this is, I think, one of the more promising sensors that I've seen. It was developed by John Valkens of Colorado State University, and it uses intentionally very low-cost, publicly available components to give you a time-integrated wearable PM sampler that has a cyclone that can do higher or lower flow sampling. So the cyclone is here, so it's got the PM 2.5 inlet, and then it's very small. You know, you're looking at 9 by 5 centimeters roughly, and it also collects a lot of ancillary information that's useful for understanding the conditions that might cause formation of PM, like temperature, precipitation, relative humidity, global positioning systems, and mass flow. So this is just the sort of components of it, and they did fairly extensive calibration so they can show that, you know, within the cyclone, the fraction that they're getting in is very similar to what you get out of a reference instrument. You get about 48 hours of wear time on the low flow and 24 hours on the high flow. And for me, that's sort of the baseline. You need to get somebody through the day so that they can recharge it at night, or they're not going to comply. They're going to forget, it's going to run out of batteries. And when you look at the validations here, they're really quite good. So, you know, this is based on an EPA in the lab where they have a 3 by 3 meter particle chamber. You're getting, you know, 0.996 R squared with the federal reference method monitor. Now, there's a little bit of bias in there, but, you know, it's not terrible. And then with Harvard Impactor in the field for a wood stove study that I think is being led by Mike Brower at the University of British Columbia, you know, 0.84. So really good correlations. They've set it up now so that you can do it outdoors. The total cost of this instrument is about $500. They've done limited outdoor cross-validation with a beta attenuation monitor, which is a federal equivalent standard. You can see they're getting pretty good correlations between their monitor and the federal monitor. So this is a filter-based instrument. The limitation here is you're losing a lot of what you want for that personal monitoring because you want to see that time data so you can then link it up, as we did in Spain, to the activity levels and get to the inhaled dose. The advantage, though, is that you can also take that filter and you can do chemical and physical speciation of the particle, so you're going to get a lot more information out of that. So let me show you an example of some monitors that we've used around the Aliso Canyon natural gas leak. Most people in California have heard that. Is there anybody that hasn't heard of the Aliso Canyon Porter Ranch gas leak? It's funny because I go to international audiences, nobody's heard about it. You know, it's sort of like, even the East Coast. What? Oh, is that in the New York Times? Yeah. Okay. You know, that's right. But anyway, it was one of the largest leaks of methane or natural gas from a storage facility ever recorded. Resulted in the evacuation of 7,000 people and 2,000 students were displaced, and many thousands were made ill during the event and continue to complain of symptoms today. If you want more detail, it's written up in a really great article by Nathaniel Rich, a best-selling author. It came out with my team for a day, and he's calling it the invisible catastrophe because it really, methane is invisible. Talked to other colleagues, and we thought if it would have been a big black plume that looked like this, it would have really captured people's attention. But you know, because it's coming out, seeping, it doesn't really seem like there's anything going on. But based on sort of a long-term collaboration I've had with Rod Jones at Cambridge University, I said, this looks like something really important is going on. Can we borrow some of your monitors? And he calls these as SNAQ boxes. So they're sensing networks for air quality. And you know, if you wanted sort of a general duty instrument that you can throw out there in a hurry that's going to measure a lot of things, and in a disaster you don't know what you're dealing with, right? So my first rule is measure everything you could possibly think of, because we don't know what's coming out of this underground storage facility, whether it's particles, gases, both. Well, we know the gases are coming out because there's methane. But this is the AlphaSense particle counter. It was developed by Paul Kay of the University of Staffordshire, a very smart geophysicist. It allows you to do size-speciated particulate matter in 16 bins, which I'll show you in a second. And then you get all these other pollutants as well. So this is the Aliso Canyon complex, and these are active storage wells that are being used. They also have oil and gas production that's going on, both with hydraulic fracturing and conventional methods. It's actually the old Getty oil field, you know, the Getty Museum fame, the Getty oil. So what I haven't shown here is there are a whole bunch of cat wells in the community as well. The community really didn't like seeing that. But this is where we had our SNAQ boxes, and we had 5 of them in the community and 1 in Northridge to sort of act as a negative control away from the site. This is what it looks like when it's deployed in someone's yard in Porter Ranch. So really, you know, not very intrusive. They weren't living there anyway, they'd evacuated. And this is what you get. You get 10-second data, and this is the ensemble of all 6 sites. So each one of these colors is a different monitor. And one of the things that jumps out at you here is for monitors that are fairly close together, we're getting very different patterns. And the spikiness that you're seeing, particularly in some of the green and purple, these are the ones that are near the site. So we started thinking, you know, we put these out and the particle monitors were on them. We were really interested in the volatile organic compounds. Started thinking, my goodness, something's going on here. Something's emitting particles near that site, because the monitors that are either downwind of where the leak was or very close to it are giving us very different signals than what we see elsewhere. Now, one of the things I should mention is that, you know, this requires a calibration. You're counting the particles, so you have to make an assumption about their size and their weight. And that's highly dependent on the humidity in the air. So you really need somebody that's almost got a PhD in atmospheric chemistry to really filter through this data, which we did have, fortunately, with Rod's group. But there's a lot of post-processing that goes on to get to this point. And then I mentioned all the size bins. So this starts at 0.38 to 0.43 of a micron, is 0.43 up to about 0.55. And it goes all the way up to about 15.5 microns. And this is just showing how much, you know, information we're getting out of these small bins that we just wouldn't see if we were dealing with the larger particles. I can't see it here, but 2.5 starts around here or here. So if we weren't using all these bins, we wouldn't have started seeing the differences between what was leaking out of the site and what was potentially, you know, background. Because we do get these sort of regional signals that pervade all the bins. Now, Rod's taken this on and gotten some funding from the Medical Research Council. This is smaller, but it's still kind of clunky and big. But he's put, you know, an accelerometer, a global positioning system in it. It has a GPRS for sending information back remotely. And then it has all of the same equipment that was on that much bigger monitor that I've shown you. And I talked to Ben Barrett at King's College last week at the HEI conference, and he's been having people with COPD carry these around, and he's getting some very interesting results about the types of environments that seem to trigger their symptoms, which you couldn't get if you didn't have a small enough monitor. Now, these are still pretty big, but as he said, the people are really sick, so they're very compliant. They'll carry anything as long as it doesn't strain them, right? So, but we want to go to something smaller, so we've been working on this idea where we really get rid of a lot of the storage and electronics, and we just have it in a fanny pack, and it feeds it to the phone so that the individual, if you want to let them see it, can see what the particle counts are like in their current environment on their phone. One of the issues here, though, when you start working with wired versus wireless, is you start losing some of the packets, right, as you're sending information across the wireless network. So we're still trying to improve that, but this shows you the difference between, you know, hardwired to the computer and then being sent through the phone. And we are getting this negative bias. We're picking up a temporal pattern that's very similar, but it's biased, so we'll have to do some bias corrections in there. But then it will immediately, when it comes into contact with any Wi-Fi signal, send information to the server so that we get these are the same 16 bins that I showed you before for that big clunky device in Porter Ranch. But now what's happened is the equipment has now gone down, and I was hoping I would have one. My friend John Saffel, who's the director of science at AlphaSense, promised to send me one of these in early April, but I guess like many bleeding edge technologies, he's a little bit behind. But I did see this, and it's about the size of my index finger. So that'll do everything that big clunky thing did in Porter Ranch, give us 16 bins of particles every 10 seconds. And the minute we can build that together with something in the phone, you can start to see where this is going, right? We're going to have these monitors built right into our phones, probably within about 3 to 5 years. So we won't have to carry a separate instrument, but even if we had a separate instrument that's that small, it's very appealing, and the type of information it can give you is a lot more than we get out of typical government monitors. So some of the lessons, we're able to get pretty decent correlations out of these instruments with reference instruments, but there's bias, they're unreliable, so a lot of them clog up, and there's extensive post-processing. So one of the things with that new version that John is grappling with is it's when they use it in Beijing, the air inlet is plugging, right? They need something to filter it, because if you're up to 400 or 500 micrograms per cubic meter, a small inlet like that is not going to last for very long. As I mentioned, the conversion to mass concentrations is tricky. And so it's big assumptions about the particle size, the atmospheric conditions. And we did some of our original conversions to mass for Porter Ranch based on the English conversion factor, and then we went out and co-located at sites in Los Angeles. I could see, you're off by 20–30% if you don't have a localized kind of conversion factor you're using. So this is a big issue, and it's one that's not easily handled, and it requires a lot of post-processing. And because of that, the low cost of the sensor has to be counterbalanced against the high cost of the human resources that are needed to go in there and clean up all the data. So I'd say, the state that this is at now is that they're not really feasible for large studies, but they're potentially very useful for smaller studies, for disaster management, where you do have, fairly sizable dollars to invest. And then I want to talk now about, I think, a very promising different type of sensing, embedded or ubiquitous. And this is building on a whole citizen science movement, and in geography we call it volunteer geographic information. So citizens are often very interested and attuned to the environmental exposures they're facing, particularly if they think that those exposures are affecting their health or the health of their children. And that motivation creates a huge resource that researchers and governments can draw upon. And a good example is all of the volunteer weather observers, the Underground Weather Network. I mean, we get incredibly resolved weather data from people that are just hobbyists that put a weather station in their backyard. So for Aliso Canyon, we had probably 20 more weather stations that we could use in a very complex terrain area where you've got the Santa Susana Mountains right there. And that allowed us to do a much better job on wind fields. Well, we can use the same type of energy and interest to measure particulate matter. And this is a study that's being led by Paul English, the Department of Public Health, and funded by the National Institute of Environmental Health Science. And I guess Edmund Cito deserves special credit here for doing a lot of heavy lifting on the technical side, and Luis Olmedo for doing all the community organizing. So this was the launch, and this is in Brawley, so I should have given you a map, but we're basically about 2 hours drive east of San Diego, right up against the Mexican border. And it's an area that regularly experiences exceedances in the National Ambient Air Quality Standards and the California Air Quality Standards, because they do a lot of agricultural burning. And that creates very dense plumes that are hard to predict where they're going to go, and also very difficult to monitor with conventional means where you might have 5 government monitors. So these are for non-regulatory monitoring. They're to give people in the community information about the risks that they're facing. And we decided early on that we didn't want this to be something that was going to be, developing our own monitors. So we took a low-cost particle counter, the Dialos, that's on the market. I think it was developed by Rufus Edwards, and I think Rufus used to be a student of Kirk Smith, so it has a connection here to Berkeley. Then we used small computers and other environmental sensors for temperature and relative humidity, which we deemed were important for doing that post-processing correction. Wireless networking, and then we made a fairly robust enclosure that was going to survive a lot of the extreme heat and winds of the Imperial Valley, and then there's an internet database that shoots things to the cloud at the University of Washington where they process the data. But probably the most important part of our endeavor here are the citizen scientists who devoted so much of their time and energy to go out and monitor the environment, put these up. You know, we had maybe 2 people that were being paid, but we had at least 15 that were donating time, going out there on their weekends and making sure these monitors were functioning properly. And I think that, you know, the potential for that kind, I mean, there are a lot of issues with it that maybe we can discuss, but it has huge potential. So we wanted to evaluate the quality, so we co-located with the cooperation of CARB and the Imperial Valley District. And then it was interesting too, as a political note, that the Imperial Valley District, Air Monitoring District, didn't want to, you know, collaborate with us at all. They didn't like the idea that somebody was all of a sudden going to have other information that they couldn't control. CARB was much more mature about it, but and helpful. And we co-located them with the beta attenuation monitors. And we had a technical working group that was advising us that comprised people from CARB and academia and consulting. And we get a pretty good prediction. You know, it's relatively linear. The R-squareds here are in the range of 0.8. We're getting some over-prediction at the high end of exposure, but really probably pretty usable information that's quite comparable, and we can do other bias corrections. So one thing we did find is that there is bias, and it's dependent on the site. So you can see at this Steely site, we're getting nearly identical information, but you go to the Kennedy monitoring site, and the Dialos is predicting levels that are about half on average of what they were for the EBAM. And this must have been during a period when things were quite low and we weren't picking up those agricultural burns. But you can see there's definitely bias in there, and it's variable by the site. So that makes it tricky to interpret the data and to know how it's going to compare to gold standards. But if you're just interested in picking up events when you should be warning people, you go from a network like this, which is the government monitoring network, to one like this, you're going to have a lot more information. And Edmund Cito has just prepared a paper trying to look at how many episodes we can detect that the government monitors don't, and it's a lot more. You know, I don't want to give away his punchline on this, but they're substantially more, and there's a lot of redundancy in there. We maybe have more than we need in some places because it'll get picked up by 5 or 6 monitors that are close to each other. But what it also allows us to do is develop very highly resolved pollution prediction models. And this is essentially a land use regression model that's been smoothed over with a kriging surface. So we're taking the pollution values by the day, and then we're saying these are the dependent variable in a regression model that's then going to use adjacent land use and emissions factors to predict. Because we have the land use and the emissions factors everywhere, we can then create a surface that gives us a highly resolved prediction. And you know what this is showing for PM10 is that we have these very small events that are going on. Spatially they're small, but the levels of pollution that are being observed are quite high. In this case, sometimes more than 325 micrograms per cubic meter if you're near one of these agricultural burning events. So I think, you know, the higher spatial and temporal coverage that we're getting could lead to much better predictions for epidemiological studies and for citizen science. The accuracy of these monitors is not always going to give you government-grade information, and there's a real issue there about how you massage that when you're going out to the public, because you don't want to unduly alarm people. You can't really do an air quality index per se, because you don't want them getting, oh, the government says it's okay, but the monitoring network says it's not. So we grappled with that quite a bit and tried to do something that's on the website explains the differences, but you have to wonder if people are really grasping all of it. And I think working with the communities can be very time consuming, but it's also very rewarding to see the level of commitment that people are putting in. And I think it builds up a broader environmental consciousness in the communities that has benefits that go beyond air quality. There's a social capital component here that's very rewarding. And I'll be going down for one of the last meetings, leaving tonight to go to Imperial Valley for tomorrow morning. And I guess, if we look at using these volunteer citizen networks for epidemiology or for other purposes, there's a big issue about the sustainability of the network, because our grant runs out in 8 months. And then if nothing else comes in or no other government agency steps in, we'll just have to tear down the monitors and, start from scratch again at some other point. This is in no means a plea for funding, but I think it just highlights that these monitoring networks are sort of new. This is the biggest one that's operating in the United States. Hopefully somebody will step up to the fray, but at this point we don't know who that is and whether it's a sustainable network. Thank you. So let me just make a few overarching conclusions. So I think the location of physical activity that's an essential component for linking to model or measure environmental exposures, and we can get high quality information. And we did a whole bunch of validation studies. What's on the phones is just as good and oftentimes better than what you get out of standalone instruments for location and physical activity, because the phones are able to triangulate with other cell phone networks. They're able to get a fix faster than a typical GIS. So it's possible to get that from smartphones, and it really can improve exposure assessments for PM and other pollutants. I think the variable type and quality of the sensors on the phones presents a lot of challenges, and that's a research area that we have to work on to try and figure out what we can do, and maybe there's something to work with the industry to standardize their phones a little more, but they always want to have the next best thing because they're in competition with each other, so not sure where that one's going to go. But I think we show that you can really improve the exposure assessment with that kind of information. I think we talk about direct personal sensors. They're not quite there yet, but they're likely in the near term, and they're likely to be wearable and awearable. In other words, they will know where they are in relation to other features of the environment. So we can set it up so that, for example, if someone's asthmatic and they're getting near a road, they may not have to have the monitor on all the time, but if they're going into a zone which we suspect would have higher pollution, we can have the monitor turn on and then give them information that may allow them to protect their health. I think the embedded sensing or ubiquitous sensing is now possible for many types of air pollution, but particularly for the particles. The gaseous pollutants have a lot of cross-interference. They're mostly electrochemical sensors, and they're very difficult to get clean signals out of. And I was on a study as an advisor in Europe called CitySense, where they spent millions of dollars. And the best they could do is a methods paper to show you how hard it is. And that's no criticism of them, they're great scientists, but the monitors just aren't there. I think the citizen science and the volunteer geographic information, as I said earlier, they show tremendous promise. So I think we have to think of these monitoring systems and the sensors as they're embedded human machine systems, right? And if we don't get the people part of it right, the monitoring probably isn't going to work as well either. And many people have contributed to this, even more than are listed here, and many people funded it. So thank you very much for your time. It's always a pleasure to be back in Berkeley.
And before I ask if there are any questions, I left out a key part of my introduction of Mike. This symposium is being put on by the Northern California Center for Occupational Environmental Health. Mike is my counterpart in the South, runs the Southern California Center for Occupational Environmental Health. Always a pleasure to have you back. Any questions? Stephanie.
Can I just ask you, so are people, your volunteers are they actually downloading data from there, or your dialysis is communicating?
Yeah, the dialysis is communicating with, there's some onboard limited storage, so if it goes down for a few days, we know it goes down because it stops sending the signal. they would go out and try to collect the monitor and download what was there. But in general, it's going up, through wireless. And
Do
then,
you have like an uninterruptible power supply for them, or, because I know dialysis is a big shut off, won't turn back on and keep them.
we don't, but we have an army of volunteers that go out in a hurry, so that helps.
Drew? Yeah.
I'm curious if you've thought about using indoor sensors as a way to keep tabs on population exposures, or if it sort of just seems like too big of a hurdle to actually extrapolate indoor concentrations in a few homes to populations at least.
Yeah, that's an interesting question. I mean, I think it's equally important to know about what's going on in the indoor environments. My sense is from doing the Porter Ranch, after we found out there were likely particles going in there, there's a whole other part to this presentation where we went and sampled in 111 homes, and public health spent a lot of money, $1.5 million on the sampling. There are a lot of indoor sources, so it's hard to generalize, to the outdoor environment from the indoor, but I think it's important to know, and that is an area where it's an easier place to monitor because you're not having such dramatic changes in humidity and temperature. And those are the things that really throw off the calibration, a lot of these instruments when you go indoors and outdoors, you're carrying them. So I think, that would certainly be another complement to this, maybe not a replacement. And then the other thing that I would say that, the EPA will always say is we don't regulate indoor air. Unless it's in an occupational setting, perhaps, and then it's OSHA.
Can I put the question on its end for a follow-up question?
Sure.
So earlier Kathy spoke about misclassification, how it can have a big impact on epidemiological studies, exposure misclassification, sorry. So the fact that people spend about 90% of their time indoors, and most of these measurements are outdoors, and you did this great study of showing activity-based exposure versus home-based exposure. That was all outdoors though, right?
No, we had indoors as
Okay.
well.
Yeah, so
And in vehicles as well, so.
do you think we need to move towards an indoor, maybe not regulation, which is too hard, but to understand epidemiologically the population impacts?
Yeah, definitely, and, the sort of infiltration rate as well of what's, from the outdoors to the indoors. And I think that, the focus on the outdoors has been because that's what the government regulates. But, if we look at where people are going to get a lot of their exposure, but as we showed, when it's activity-based, it tends to drive down the importance of that home location. But,
Yeah. Drew's got some ideas about how to monitor the indoor environment, so you should talk about that. So Suzanne?
Thanks.
Really quickly, what was the source, do you think, of the particles that you saw at the Parker Ranch?
yeah, so we did, we used an electron microscope and somebody was very skilled, so we got some of the mud that was from the leak site and compared it to the particles that we collected from dust swipes indoors. And we think that what was happening is essentially these storage facilities they're depleted oil fields. So around January 7th, Governor Brown issued, an emergency declaration and ordered the gas company to stop putting any pressurized compressed gas into it. So they went down to what's known as their cushion level. So they're at, maybe 20% capacity. And at that point, the gas and the oil are very close together, and it's coming out under very high pressure. So we think it was probably very small oil droplets. We also found evidence that there were heavy metals like barium and strontium that had entered the houses. So we didn't get as many elevations of VOCs as we expected to see, but we worked statistically to find a cluster of these heavy metals, which we see as a fingerprint that there was probably intrusion into the house from these particles. And when I was sampling some of the areas, I really wish I was wearing protective gear after, it was like an oily substance when we put the swab to it. And they were running in the range of about 2 microns in size. The other hypothesis is that there's enough gas coming out that within about 2 kilometers of the site, you could see the formation of secondary organic aerosols. And we haven't, made any firm conclusions on that, but I think based on the electron microscope analysis plus what we saw in the dust swipes, it's probably the oil that was coming out. And then some of it was probably from the kill attempts earlier on in the event. So basically got some, oil people from Texas to come in and say, how do you do it? Well, they take huge barrels and they fill them with salts and a lot of heavy metals, and they shoot them down under high pressure. And then if it doesn't work, what happens is that sprays out, and there was a lot of evidence of residue that was going on people's cars and houses that wouldn't come off, so it was some kind of acrid substance. And one poor gentleman had his brand new Mercedes completely ruined by it.
Porter Ranch is not a poor community.
It didn't look like it.
You're aware they're selling the houses for more than they were selling for them before?
I wasn't aware of that, but
Right, well, I think we're gonna cut it off here because we have to, okay, Addie, one more question.
Can you talk about indoor air systems that you're aware of for high pollutant areas? So for instance, green buildings where possibly retirees could live. We've got this terrible air basin in Sacramento, large population. Can't we do things with technology to protect the public against this higher incidence of cardiovascular disease?
yeah, well, I'd say I'm not an expert on air filtration, but certainly, in my own house, I have HEPA filters running. I have HEPA filters on the furnace. So you can put in what might be called hospital-grade filtration. The problem is in individual dwellings, a lot of people like to open their windows. So there's a preference for feeling that outdoor air, and they feel like it's stuffy. And I think we talked about this earlier. Debbie Bennett of UC Davis has done several studies where people get subsidized to use these air filters in highly polluted areas. And the biggest problem is, and maybe it's sort of like the stoves, and the stoves, they like to keep using their polluting stoves. With the air filters, they still like to keep opening their windows, and they completely destroy the efficiency of the filtration system when that happens. But you can do that. You can do a lot to tighten up the architecture of the buildings and the windows so that they're not letting in as much infiltration. But a lot of it, again, depends on the human behavior and whether people are going to comply.
Okay, so, thank you, Michael.